how this is set up, I know for sure that people have stood here and talked and told stories and taught lessons, and it makes it a great time and space in the footprints of the ancients, this nature that we inherited from them through all the different ways that we got to be here. And this one here is ours now. This is the one that we have the opportunity and the ability to interact with, and what we can do for our interaction to improve.
This seminar is an interactive meditation on the relation of the self to nature. Please speak with your own opinion rather than play devil's advocate. Speak what you think and phrase as a question otherwise. Avoid asking, "Don't you think?" but ask, "Do you think?" The content of the presentation is what I think. There are 3 components to a coordinated interaction: thought, speech, and action. The first session is to illustrate a thought pattern regarding our place in the universe, all the way down to the physical presence at our feet. Consider the limits of our perception and limits of our abilities. Tomorrow we will talk about application in the field, and you will have time to interact with the forest on your own. Sunday we will hike into the valley and discuss ability and opportunity for human action at the macro scale. Consider things in the following terms: time, distance, energy level, ecological function. For a whole view, we will start the image from the beginning. At first, all energy in the universe is confined to a point. This is the lowest energy point in kinetic energy and highest in potential energy. This is also the lowest temperature, as in no relative motion or absolute zero. The biggest mathematical leap is from nothing to anything relative to the leap from anything to anything else. When all the potential energy in the universe released from the standstill of absolute zero, it immediately reached the highest levels of kinetic energy and highest temperatures, pushing forth the dimensions of distance faster than the speed of light. When differentiation occurred, time became relevant. As the dimensions of distance widened, the energy settled into high-energy photons, and those precipitated through pair production into electrons and positrons. These are isometric packets of energy with speed less than the speed of light, creating mass and gravity. As the particles slowed further, they dropped to the next isometric measure, protons, which have more energy per packet at a lower speed. These coalesced further into the first giant masses of galaxy-sized stars and quasars. This marks the end of the original cooling and start of the new localized heating points. The proton masses attracted and crushed together, generating the pressures required for direct proton-to-proton fusion. Their masses quickly grew under the force of gravity and slowed further from the speed of light. Gravity compressed the cores with pressure that caused electron absorption and created neutron mass in the core. When the pressure surpassed the energy required to keep the neutron walls together, these heavenly bodies collapsed into the first massive black holes. This drew a tremendous vacuum, resulting in a shock wave that blew off the outer layers of hydrogen clouds, and then will coalesce into elliptical galaxies and the first-generation stars composed of hydrogen. First-generation stars compressed energy into smaller packets by direct fusion reaction of hydrogen into helium and then to subsequent elements until iron. As the star cores grew in density, the iron cores absorbed electrons to form neutron mass. When the gravity of the neutron mass exceeded a certain threshold, the core collapsed into a black hole, creating a shock wave that threw off the outer layer of the star composed of elements from hydrogen to iron. The shock wave also forced matter together to form heavier elements, the heaviest radioactive stable element being uranium. The new matter coalesced into second-generation spiral galaxies like our own. Much of the galactic mass is concentrated into a supermassive black hole in the center, forming the center of gravity that tethers the stars and loose mass that spiral around. Mass disturbances from heavy elements swirling around in clouds of hydrogen cause accretion of stars from the nebula, and when these groups of stars light up, their solar winds push each other apart to settle into their galactic tracks. These second-generation stars are composed of mostly hydrogen, but there is enough other heavier matter that instead of direct proton-to-proton fusion, the stars run on the carbon-nitrogen-oxygen cycle that turns hydrogen into helium. Once the hydrogen is depleted, the stars swell and cool as elements build up to iron. Without sufficient mass, the star's nuclear reaction will stop, and the remaining mass will cool. If mass is sufficient, all the core's mass will undergo electron absorption, and the core will collapse into neutron material and eject its outer jacket. If the mass is large enough, it will collapse past the limit of the neutron sphere and into a black hole. In the closed theory of the universe, as energy keeps condensing into mass and the mass becomes trapped in black holes, the black holes will attract each other and drift together to combine into one big black hole with gravity such that it pulls in all the remaining energy from the universe and pulls back the dimensions of distance. Time loses its relevance and all returns to one, as all the kinetic energy returns to its potential. Our star formed about 9.1 billion years after the Big Bang, or about 4.6 billion years ago. Formed in a mostly hydrogen nebula, the Sun with its solar wind cleared the nebula and settled into its galactic position. Some heavy elements that were in the Sun's gravity field did not fall into it. Instead, this material accreted into planetary masses. Our planet coalesced from a relatively cold dust of mostly iron, nickel, silicon, calcium, magnesium, oxygen, and other elements. When the planetary mass pressed together, the compression generated heat that melted the material and it settled into strata: inner core, outer core, lower and upper mantle, the crust, and the atmosphere. The crust cooled to rock about 3.8 billion years ago, and about 300 million years later, single-celled organisms appeared where surface water was present. There are three prevailing theories as to how the water got here, and they could all be true. The original water that accreted with the planet evaporated and remained suspended in the atmosphere until the crust cooled. The water arrived after the crust cooled in the form of comet showers, and that the decay of radioactive material by proton ejection and other free protons combined with the abundant oxygen atoms to create water. Early life also combined elements such as hydrogen sulfide and carbon dioxide to produce sugar, water, and sulfur. About 1 billion years after first life, or about 2.5 billion years ago, enough water accumulated on top of the crust that the pooling put pressure on the crust and it started to crack, and the continental plates started to form. Major abundance of single-celled organisms was present by about 2 billion years ago, and the first multi-celled eukaryotes appeared about 1.8 billion years ago. About 1 billion years ago, there was so much photosynthetic activity that the concentration of oxygen in the lower atmosphere rose to the point that it tipped the evolutionary balance, and there was a sharp decline in single-celled organism colonies and a sharp rise in multi-celled eukaryotes. The growing continental mass first coalesced at the equator around 530 million years ago and gave rise to an abundance of soft marine eukaryotes. Within the next 30 million years, the continental mass shifted toward the South Pole, mostly submerged. Here, there was another significant rise in eukaryote population and complexity, including the first land plants. Then, about 50 million years later, the continental mass settled on the South Pole and massive glacial ice accumulated, lowering sea level, and the second massive die-off occurs, including 3/5 of all marine invertebrates and about a quarter of all life. About 30 million years later, or about 420 million years ago, there were massive glacial melts, substantially raising sea level and giving rise to the first salt and freshwater fish, land critters, vascular plants, and corals. Within the next 80 million years, or about 350 million years ago, the continental mass split and what will become the North America, Europe continent drifts to the equator, mostly submerged, and major evolutionary advances occur, including first trees, first seed-bearing plants, first land vertebrates, and wingless insects. Within the next 50 million years, about 300 million years ago, the Siberian continental plate collided with the Europe-North American continent, and then a second collision with the South American African-Arabian continent. Now there was also a great increase in life, including the first large forests, the first land eggs. This is when the first coal deposits occurred. Over the next 50 million years, the continental mass coalesced in a continuous mass from the North to South Pole, and then the third massive die-off occurs and is most massive among ocean life. Then the first large seed-bearing forests occur, and then, about 40 million years later, the fourth and even more massive die-off occurs, after which the conifers and the dinosaurs rise. By about 145 million years ago, the single continent starts to break up, and there is the most biomass, including the first flying dinosaurs and birds. At this point, the oil fields begin to form. About 80 million years later, or about 65 million years ago, the Earth is struck by an asteroid, and the dinosaurs along with much of life goes extinct, and gives rise to the first flowering plants, many of today's birds and insects, and the mammals begin to rise. By about 40 million years ago, most modern mammals appear and grasses begin to appear. About 10 million years ago, there was a major climate change when the African and Arabian plates joined the Asian continent, and Antarctica is isolated in the South Pole. The Antarctic continent collected significant ice, and there was a significant cooling and drying event. A circumpolar current was established, and ocean water mixing was reduced significantly, and kelp forests and grasslands first appear. About 4.4 million years ago, the first hominids appear. At about 3 million years ago, there was another major cooling event accompanied by significant polar ice and drying of the land. The Stone Age begins around 2.5 million years ago, with a stone axe being common around 1.3 million years ago. About 1 million years ago, a major warming period began. Many large mammals went extinct. About 500,000 years later, hominid use of fire begins. First anatomically modern humans appear about 150,000 years ago and have spread throughout all the continents except the Americas and Antarctica by 40,000 years ago. The Neanderthals first appeared about 120,000 years ago and disappeared around 28,000 years ago. The coldest phase of the last ice age began around 27,000 years ago, and it peaked at about 20,000 years ago, and then started a warming period about 16,000 years ago. At about 14,000 years ago, intensive harvest of cereals by humans begins. At about 13,000 years ago, the megafauna, including mammoths and woolly rhinos, went extinct in Eurasia and would go extinct in the Americas around 10,000 years ago, accompanied by a significant retreat of the ice sheet in Eurasia and North America. This retreat of the ice sheet continues today. There are things that we can control and things that we cannot. As people, we have always pushed these limits. The last 65 million years set the last reset in evolution that set our stage with microbes, invertebrates, fungi, fish, plants, and animals. The major evolutionary advances of this era are mammals, flowering and fruiting plants, and grasses. From the time people discovered the use of fire about 500,000 years ago to now, there have been several ice ages and big changes in sea level accompanied by changes in animal and plant composition. Large groups of people in cities and roaming tribes became a significant force in nature, and unmechanized people accomplished great feats harnessing the forces of nature. Nature has shown booms and busts. We as people should gauge ecological health, sustainability, and diversity to avoid a fate similar to collapsed societies of the past. People have a higher order of complexity related to background creatures by way of ability to communicate and record and refine actionable information. This way we can recognize trends over time and generations, and our thought process transcends the individual experience. Since the Industrial Revolution about 400 years ago, people amassed specialized understanding of the physical laws of nature and used it to mine the earth for building blocks, as if the earth is a stationary parts store rather than a living system. Our rate of consumption continues in an accelerated crescendo, with depletion rates clearly registering on the whole system scale. To avoid a natural bust, we need to look at adjustments to our interaction with the whole system. So let's consider ecological function. People reached the Americas relatively late, at about 12,000 years ago. The glacial retreat that occurred in Eurasia about 13,000 years ago was happening in North America about 10,000 years ago, and marks the final decline of the megafauna. Palomar Mountain appears to have been settled by humans at least 5,000 years ago. This mountain is a granite uplift from the former plains. This creates an uplift that lifts the moist air blowing onshore from the Pacific and precipitates rain, the essential ingredient for life. Water will condense in the presence of any surface below the dew point. When water falls on bare soil, it will percolate down to the aquifer, will run off, or will be evaporated by the sun. A prime constituent to life is to retain water in a body that resists gravity. The basic building blocks for these bodies are hydrogen, oxygen, nitrogen, and carbon, just like the sun's CNO cycle, in the form of fat, cellulose, protein, and sugar. There is a special relationship between these elements that compose life on Earth. Oxygen is abundant on Earth from the inner core and out. Hydrogen floats up, and if it is not bonded to another element such as oxygen to create water, it will percolate the atmosphere and get carried off by the solar wind. And it's also replenished through proton emission, a type of radioactive decay. Carbon is a bit more anomalous. Carbon does not appear common below the crust, and there was relatively low concentration of carbon during Earth's initial accretion. There is evidence to suggest that the carbon concentration at the surface has risen over Earth's lifespan. The prevailing theory is that the added carbon comes to Earth from outside, primarily in the form of carbonaceous chondrites. When these meteors strike the Earth's atmosphere, the carbon fuses to oxygen in the air and reaches its lowest energy state, CO2, which settles to the lower atmosphere. The partial pressure of CO2 in the atmosphere drives carbon into the oceans in the form of carbonic acid, CH2O3. Life-containing chlorophyll can take carbon dioxide, 6CO2, combine it with water, 12H2O, and output oxygen, 6O2, and glucose, C6H12O6, empirically CH2O. This is the basis for most organisms and organic chemistry. The sugar created from photosynthesis is metabolized and forms more complex carbon chains such as fat and proteins that form both hydrophilic and hydrophobic surfaces. Marine life can also combine carbon with calcium to form calcium carbonate, CaCO3. Organisms metabolize organic material and respire CO2 by combining the carbon atom from a sugar molecule, CH2O, with O2 to produce CO2, carbon dioxide, H2O, water, and heat. The mass balance is such that a lot more carbon is captured by organisms, concentrated, and is isolated from the atmosphere than is respired. The carbon consumed by life in body and excrement is removed from the partial pressure equilibrium between the CO2 in the atmosphere and the carbonic acid, CH2O3, in the oceans. Plants pull water and nitrogen from the ground, use light from the sun to combine it with CO2 from the air, and release O2 and water vapor into the air. This action causes evaporative cooling and reduces plant cell temperatures below ambient and has a cascade cooling effect in the shaded area. When a plant surface drops below the dew point, the leaf surface condenses water. While water in the atmosphere can condense on the surface of dust particles to precipitate rain, the surface to volume ratio of a pollen particle is much greater, so that a lot more precipitation can occur in the presence of a forest. The forest increases the stationary presence of water in the following way. Rain falls in the forest and percolates down to the ground and is absorbed by carbonaceous material. When it evaporates from the soil and strikes the surface of a leaf below the dew point, it condenses and drips back down to the ground. Water that evaporates above the forest canopy, including by evapotranspiration, can be recaptured by forest particles and return as rain. Animals in the forest consume and concentrate carbon-based material in the forest. Their deposits mix with the material on the surface and create hydrophilic water sponge material and hydrophobic membranes that keep water on the surface. This regulates surface water. This way, the forest brings rain, retains water, controls its temperature, and provides food and shelter for its ecosystem. Optimal ecosystem health is a system that has well-regulated water and temperature, abundant variety of life forms with a low parasite rate. A parasite is a relation between organisms where one organism takes a relatively small amount of material from another and causes it reproductive harm or death. With a variety of life forms, a lot of creative niches can be filled in the forest to perform the primary function of life, to pull carbon out of the air and deposit it in an inanimate non-CO2 form. Example, a tree uses sunlight to absorb CO2, combine it with water to produce glucose and oxygen, and cooling thermal energy. Plants build complex carbon material that feeds animals that break it down and excrete it onto the soil. This makes nitrogen available in the soil for the plants, disperses and fertilizes plant seeds, and sinks carbon into the ground. Predators and scavengers regulate the presence of unhealthy parasite host members among a population and reduces carbon to the soil through body and excretion. The local ecosystem on Palomar is a 5-million-year-old watershed in Southern California. As the mountain pushes up, the granite block pushes the former plains crust out of its way, and the updraft it causes brings rain. The mineral slurry mixes with the organic material created out of the mountain air, washes down the mountain, and brings fertility to the valley and seabed below. People likely arrived at Palomar when the megafauna was still here 12,000 years ago and survived through the decline and extinction of the large animals. Before the Spanish arrived, this region had a patchwork of tribes that had established summer and winter rotations over the region. There is evidence of human habitation at the Harrison Serenity Ranch for thousands of years, where people would typically camp during the summer. People fanned out about the land and moved back and forth across the land seasonally, performing an ecological function in regulating certain aspects of the land for their own nutritional benefits. At some time between the establishment of the Spanish mission and the creation of the state of California, the local tribes were deprived of their traditional routes and were confined to reservations. The government of Mexico and then the state of California gave land grants to new settlers, Nate Harrison being the first on this land. By now, the ecology has changed. The practice of the people stopped facilitating the flow of carbon-absorbed material from the mountain to the ocean. With insufficient large animal interaction in the forest, tree limbs and grasses dry and cast a dark shadow on the ground below. Without enough demand for the organic material produced by the forest, the dead members accumulate and have a reduced capacity to hold water, and when the flammability levels rise to catastrophic, they erupt into megafires, further drying the land and reducing biological output. The Earth has its own internal heat source from the force of gravity against the total Earth's mass. The heat is greatest in the center and radiates outward. The heat is insulated in the convection zones of the mantle, insulated further by the lithosphere and the continental crust, and the final insulation layer is the atmosphere. The sun shines on a little less than half the Earth's surface at all times. The Earth's albedo is variable, from very high, at snow or ice surfaces, to very low, as over the ocean. These variations, along with the gravitational pull of the sun and the moon, create differences in potential energy that drive movement in the water and air. Life's place in all this is significant. The characteristic that unifies all life is that life alone resists gravity. Life can pull down in water against buoyancy and can rise up on land against gravity. With procreation, this activity is sustained against time. Life does this by encapsulating water in a hydrocarbon membrane assembled in various levels of complexity. Life alters the thermodynamics of Earth relative to what would exist under the influence of gravity and sunshine alone by removing carbon from the air and depositing it on the crust in a mineral form. This is a one-way transaction. Yes, it comes with many belches of carbon into the atmosphere and even forest fires that emit carbon and heat. The overall trajectory of carbon through life is from the air into the ground. That is, until the industrial age. Humans have been returning significant quantities of mineral carbon back into the atmosphere. This is commonly called anthropogenic carbon. There are many variables that affected Earth's climate from accretion to now. Examples of factors that we have no control over include Earth's orbital eccentricity and axis tilt, solar activity, and incident carbon flux. We know these fluctuate and show impact to climate over the deep past. However, we can affect climate by taking care of our ecological system's health. We can stabilize climate through ground cover. People have a catalytic role in the forest. Using knowledge of a few simple patterns and a few simple tools, we can sculpt our existing forests to facilitate the flow of carbon into the ground. On a large scale, this would include herd grazing that traverse all open spaces on a periodic basis of approximately once a year. This will fertilize and trample the soil and bring last year's dead material to the ground. People's ability to balance the trees will strengthen the forest and increase its biological output. Healthy forests are less prone to catastrophic wildfire. The anthropogenic geological event of releasing significant amounts of mineral carbon into the atmosphere has helped us learn a lot about the forces of nature to the point that we simulate life in inanimate objects. Instead of using this power of knowledge to enliven our living systems, we have been using it to simulate and replace the living system. We have cut down most of the land forests, dammed most of the rivers and tributaries. The biological system of Earth is experiencing a sharp decline in species and in activity. Without forest cover to cool the earth and condense water, the bare soil will heat up, warm the air, and evaporate water. The TreeCulture method induces balance in the forest. We as people each have a long relationship with the forest on a personal level through our biological heritage. We groom the trees and their surrounding community. There are a few basic patterns and techniques that are intuitive and improve ecological activity. In the next session, we will look at on-site examples and demonstrate tooling and techniques. The goal here is to spend interactive time with the forest and induce balance.